Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Master's Degree Programs. Master of Science, Renewable Energy and Environment, MSCRWE. Semester I. MRW 001 Energy Conversion. Block-2 Steam Nozzles and Turbines. Unit 5 Condensers. 5.1 Introduction. The objective of steam condenser is to condense the exhaust steam from steam engine or turbine. It can be shown that the lower the temperature at which heat is rejected, the higher will be the efficiency of the engine or turbine. In a steam engine or turbine, this object is achieved by the creating a high vacuum in the condenser, so that the temperature of condensate of the exhaust steam may be low. By providing a condenser in a steam plant is further possible to use the same water over and over again, as the condensate may be pumped back into the boiler. Owing to the formation of scales, when hard water is heated in a boiler, it is necessary to treat the hard water in water softening plant to prevent encrustation of boilers. Thus, when a condenser is used, it saves the running cost of water softening and the capital of such a plant except that when is required for the makeup water. The advantages of a condenser are summarized as follow. I. It improves the efficiency of the plant. 2. It reduces the steam consumption per H.P. R. 3. The running and capital costs of water softening plant are reduced. 4. It increases the output of the plant for the same boiler pressure and temperature of the steam. The wastage of treated water is reduced. 6. It provides for the supply of hot water to the boiler. There is, however, a limit to the increase of efficiency by creation of high vacuum in the condenser. This is imposed by the capital cost involved in the installation of plants for the creation of higher vacuum. A vacuum of more than about 26 inches of Hg is economical in a steam engine, whereas in steam turbine, the vacuum to be increased to 29 or 29.5 inches of Hg, depending on the capacity of plant and the temperature of cooling water. Available objectives. After studying this unit, you will be able to understand the fundamentals of various types of steam condensers, their working principles, and characteristics and performance. 5.2 Steady-state energy balance equation. For steam condensers, to obtain steady flow energy balance equation for condensers, let us consider a general steady-state energy system as shown in Figure 5.1. Figure 5.1. A general steady flow energy system. From the first law of thermodynamics, we can write QWXE. Look at the screen. In case of condenser, as shown in Figure 5.2, following assumptions can be made. Figure 5.2. Steam condenser. I. WX0, because there is no shaft work. 2. ZZ to Z10, because difference in the outlet and inlet levels of steam entry is negligible. 3. C0, no change in the velocity of steam. So, from EQ 5.1, the steady-state energy balance equation for condenser becomes QMHM H2 H1 5.2. If the initial and final temperatures of the water used for obtaining condensate are T1 and T2, and the mass flow rate of water is megawatt and specific heat of water is Cp, Then using the relation heat loss heat gain, we get Q megawatt CP T 2 T 1 5.3 5.3 steam condensers and condensing 5 March 2001 classification of steam condensers on the basis of the methods of production of condensate the steam condensers can be classified mainly into two groups. 1. Jet condenser. In this type of condenser, the cooling water is in direct contact with the exhaust steam from engine or turbine. 2. Surface condenser. In this type of condenser, the cooling water does not come into direct contact with the exhaust steam. 5 March 2002 condensing plant. In order to condense the exhaust steam from a steam engine or turbine effectively and to remove condensate under vacuum conditions, the following are the essential requirements. I. An air pump or ejector to remove the air which finds its way into the condenser by leakage or with steam from boiler which evaporates water containing some dissolved air. This pump also removes uncondensed saturated water vapor along with the air. Such pumps are known as dry air pumps. 2. An extraction pump which is generally of centrifugal type and remove the condensate from the condenser to a tank known as the hot well, from which the feed water pump supplies to the boiler through a feed check valve. A combination of a dry air pump and extraction pump is known as a wet air pump which removes both the air and condensate simultaneously. 3. A cooling water pump, CW pump, to supply the cooling water to the condenser for condensation of the exhaust steam. 4. A cooling water tower or pond with spray for cooling the heated water from the condenser when cooling water supply is limited and has to be used over and over again after recooling. 5.4 jet condensers. In jet condenser, the cooling water is in direct contact with the exhaust steam from the engine or turbine. Jet condensers may be classified into the following categories. I. Parallel flow condenser. In this type of condenser, the direction of flow of both cooling water and exhaust steam is the same and is in the downward direction. 2. Contra flow condenser. In this type of condenser, the cooling water flows in the downward direction by gravity and exhaust steam meets the water current in the upward direction. 3. Ejector condenser. In this type of condenser, the exhaust steam and water mix in a series of convergent cones. The cooling water flows by gravity through the convergent cones and draws the exhaust steam to be condensed through openings at the narrow ends of the convergent cones. 5 April 2001 parallel flow jet condenser. A low-level parallel flow jet condenser having a dry air pump and condensate extraction pump is shown in figure 5.3. In the parallel flow jet condenser, the mixture of exhaust steam and air from the engine enters the top of the condenser and meets with a sperry of cooling water. The exhaust steam gets condensed and flows down under gravity to be extracted by either one single pump, known as the wet air pump, which removes both air and water, or by two different pumps, one extracting the air and the other extracting the water. The later arrangement is shown in figure and gives greater vacuum. It may be of low-level or high-level type. The later type is known as barometric type and does not require an extraction pump, but requires only a dry air pump which draws out the air and water vapor from the condenser. The disadvantage of the parallel flow type is that the condensate gets cooled progressively as it goes down the condenser and, hence, reduce the plant efficiency. It is therefore seldom used, although the low-level type does not require a cooling water pump. Look at the screen. Figure 5.3 Parallel Flow Jet Condenser 5 अप्रैल 2002 Contra Flow Jet Condenser. There are two types of contra flow jet condensers. These are I. Low-level contra flow jet condenser and 2. High-level contra flow jet condenser. I. Low-level contra flow jet condenser. A contra flow jet condenser of the low-level type is shown in figure 5.4. In this type of condenser, the mixture of exhaust steam and air enters at the bottom of the condenser and the cooling water is sprayed through perforation from the sides of condenser at the top. In this case, as the cooling water goes down, it meets with greater quantities of exhaust steam and hence, there is no undercooling of the condensate if the exhaust steam inlet is at the lowest level of condenser. Look at the screen. Figure 5.4 Low-level contra flow jet condenser. The low-level condenser does not require a cooling water pump to feed the cooling pond by the vacuum in the condenser. There is a dry air pump connected to the top of the condenser where the volume of the air is reduced as its temperature is minimum. 2. High-level contra flow jet condenser. A high-level or barometric contra flow jet condenser is shown in Figure 5.5. Since the barometric condenser has a tailpipe about 34 feet high, the condensed steam and cooling water will discharge automatically into the hot well and no extraction pump will be necessary. It will, however, be necessary to provide a cooling water pump to deliver the water to the top of the condenser. Figure 5.5 High-level contra flow jet condenser. Look at the screen. 5 अप्रैल 2003 Ejector condenser. An ejector condenser is shown in figure 5.6. It consists of a cylinder of cast iron, inside which is a series of coaxial converging cones. A mixture of exhaust steam and air is drawn into the annular space between the outer cylinder and the nozzle through a non-return valve. Water under a head of at least 20 feet flows from the top of the condenser through the converging cones and increase in velocity at the throat of the nozzle, thus reducing the pressure. This reduction of pressure draws in the mixture of exhaust steam and air into the nozzle through ports at the throat of the nozzles and effects intimate mixing with the cooling water. As the water will have no pass out of the condenser, this is effected by providing the diverging cone at the end, so that the velocity of the water may be reduced at the end of diverging cone. The reduction of velocity of the water effects an increase of pressure and so the water discharges automatically into the hot well. In this case, therefore, no extraction and air pumps are necessary. This type of condenser is suitable for small engines where a vacuum of not more than 24 inches of Hg is required. A non-return valve is provided at inlet to the condenser so that in the event of sudden failure of cooling water, the water from that hot well may not be sucked into the engine. Figure 5.6 Ejector condenser. 5.5 Surface condensers. Surface condensers may be divided into the following two classes. I. Surface type condenser. In this type of condenser, cooling water flows up through the horizontal metallic tubes of brass and the exhaust steam flows downwards around these tubes. 2. Evaporative condenser. In this type of condenser, the exhaust steam flows downwards through the coil of tubes and the cooling water trickles down on the surface of the tubes. 5 May 2001 Surface type condenser. Surface type condensers are more efficient in creating a higher vacuum and, as such, are in common use in power stations. These are preferred to jet condensers, where a large quantity of cooling water is available. The larger capital cost of surface condensers is justified on account of saving in the steam consumption due to the higher condenser vacuum. Classification of surface type condensers. Surface type condensers can be classified into two categories. These are I. Downflow surface condenser and 2. Regenerative type surface condenser. I. Downflow surface condensers. A longitudinal section of a downflow type surface condenser is shown in figure 5.7. Figure 5.7. Downflow surface condenser, longitudinal section. It consists of a cylindrical shell of a cast iron with its two ends covered by two cover plates. Brass tubes are fixed to two tube plates at the two ends by means of brass ferrules for facility of replacement. One of the water boxes formed between tube plate and the cover plate has a partition separating the top space from the bottom space. Cooling water enters the bottom space and is forced to make two passes of the brass tubes before going out of the condenser. The exhaust steam enters at the top of the condenser shell and comes in contact with the outgoing cooling water, which has been progressively heated by the condensing steam as it passes from the bottom to top. As the steam passes to the bottom, it comes into contact with the tube cooled by coldest water and is effectively condensed and extracted by the condensate extraction pump. A baffle is provided near the bottom for the dry air pump suction pipe to be covered so that no condensed steam can find its way into it. The air which is associated with the steam goes first to the bottom of the condenser and then moves up to the air pump suction for effective cooling so that the capacity of the at pump may be reduced. The space enclosed by the baffle in the condenser is known as an integral air cooler. 2. Regenerative type surface condenser. The transverse section of a central flow or regenerative type surface condenser is shown in figure 5.8. Figure 5.8. Regenerative surface condenser. In this type, there are steam lanes all round the periphery of the condenser shell. The exhaust steam converges to the center of the shell where there are no condenser tubes. The center of the condenser is connected to the section of the dry air pump. A portion of the exhaust steam associated with air passes round the steam lanes to the bottom of the condenser and then moves up towards the center. In moving up, the steam comes across the cooled condensate falling through the tubes. Thus, the condensate is reheated as early as possible to the temperature of the exhaust steam and there is little undercooling of the condensate. The air associated with saturated water vapor is pumped out of the center of the condensate and the exhaust steam is drawn from the periphery of the condenser to its center so that the path of flow of steam is reduced. Thus, there is less pressure drop of the exhaust steam than in the downflow type and by proper regulation of the cooling water, it can be so adjusted that there is no more than about half a degree centigrade of undercooling of the condensate. 5 May 2002 Evaporative condenser. This type of condenser is primarily used where water supply is expensive, as in deserts, and for small generation of power. In this case, the supply of cooling water is not in such large quantities as in the case of surface-type condenser, as both the cooling water and surrounding air are effective in condensing the steam flowing through the tubes. A line diagram of an evaporative condenser is given in Figure 5.9. It will be seen that, in this type of condenser, the steam flows through a coil of gill tubes which are exposed to the atmosphere, and a spray of water trickles down from a perforated tube from the top row tubes to the bottom row and then falls into a makeup water tank. The water goes heated as it falls, and hence the surrounding air being heated flows from the bottom of the condenser to the top, carrying along with it a portion of the cooling water evaporated into vapor. Thus, heat given up by the steam is equal to the heat carried away by cooling water, air and vapor, and hence a much smaller quantity of water is required than in the surface condenser. Thus, the capacity of cooling water pump need not be large. It has, however, certain disadvantages that it requires two pumps, one for supplying the makeup water evaporated into vapor and another for circulating water. Further, the vacuum created is not so high as in the surface-type condenser, and it gives out cloud of vapor condenser tubes, which is a nuisance to the surroundings. Its advantages are that it is simple, cheap, and does not require large quantity of cooling water, and hence, the capacity of cooling water pump is small. Figure 5.9 Evaporative condenser. 5.6 Weight of cooling water required in the condensers and the vacuum efficiency. We will now discuss the quantity of cooling water required in the condensers and the vacuum efficiency. 5.6.1 Weight of cooling water required in jet and surface condensers. The cooling water is required to take away the latent heat of the exhaust steam. A large quantity of cooling water is necessary to be supplied in jet condensers and also in surface condensers, except for evaporative condensers. For the same vacuum conditions, the vacuum in the condenser also varies, as there is a pressure drop with the condensation of the steam, and in a down flow surface condenser is the lowest at the bottom. If, however, the temperature of the condensation of the exhaust steam is not specially given, it may be assumed at the absolute pressure corresponding to the average condensate temperature. Let us consider two cases. A. When quantity of exhaust steam is given, let W's weight of steam condensed per hour, W weight of cooling water per hour, X dryness fraction of steam, Tc temperature of condensation, C. H sensible heat of water at Tcc, L latent heat of steam, J. T1 inlet temperature of cooling water, C. T2 outlet temperature of cooling water, C. Hc sensible heat of condensate, J. P turbine power. Then, heat given up by steam, heat taken up by cooling water. Look at the screen. B. When the quantity of exhaust steam is unknown but that of steam at inlet to turbine is known. 5.6.2 Vacuum efficiency of the condenser. In a perfect condenser there should be no air, and the pressure in the Condenser should be that due to the exhaust steam alone at inlet to the condenser corresponding to the saturation temperature of steam. There should, moreover, be no undercooling of the condenser due to condensation. Along the condenser, the vacuum efficiency of a condenser is, therefore, defined as the ratio of actual vacuum as found by the vacuum gauge to the vacuum due to steam alone when there is no air. Thus, vacuum efficiency actual vacuum upon maximum possible vacuum. Vacuum at Intel condenser in cm of Hg upon barometric high minus absolute pressure of steam in cm of Hg. 5.12. The vacuum efficiency would be 100% if there is no air. 5.7 Summary. The objective of steam condenser is to condense the exhaust steam from steam engine or turbine. This objective is achieved by creating a high vacuum in the condenser so that the temperature of condensation of the exhaust steam may be low. The essential components of a condensing plant are an air pump, an extraction pump, a cooling water pump, a cooling water tower or spray pond, and a condenser. The performance of jet condensers depends on the following factors. I. The rate of mixing of steam and cooling water. 2. The temperature of cooling water. 3. The direction of flow of steam and cooling water. 4. The temperature of condensate. The performance of the surface condensers depend on the following factors. I. The temperature of the cooling water. 2. Velocity of cooling water in the tubes. 3. Surface condition of the tubes. 4. Arrangement of tubes inside the cell and the resultant steam space. Effective arrangement to remove air. 6. Quantity of steam condensed. Both jet and surface type condensers need large quantity of cooling water, whereas evaporation type condensers need less quantity of cooling water. The vacuum efficiency of the condenser depends on the pressure at the inlet of the condenser, barometric height and the absolute pressure of the steam. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.